everyone, and welcome to our ML math session. My name is Katrina, and I'm the machine learning math lead here at Cohere Labs. And today we have a very special session. We have our guest speaker, Siddhartha. He's a Master's of Science student at the University of Alberta, and he will be talking about matrix calculus and usage in machine learning. So with that, I'll hand it over.
Hello, thank you so much for inviting me for the talk. So today I'll be talking about matrix calculus, and to give a brief intro of me, I'm a master's student at U of A, and I broadly study statistics and machine learning theory. And right now I'm kind of looking at reliability, because machine learning models can predict, but often we don't know how good their predictions are. So that's the type of work that I'm kind of working on right now. And for the talk today, we're going to be talking about matrix calculus, which is essentially linear algebra plus calculus, and doing optimization with higher dimensional vectors like matrices and vectors. And this is my name and my email. If you have any questions, you can feel free to reach out anytime. So what's the motivation of this talk? The motivation is that we often say linear algebra and calculus are some of the most important fundamentals in machine learning, as well as probability, but oftentimes we learn them separately. We learn linear algebra on its own and calculus on its own, and we don't really see how these two are connected and how it's used in machine learning and all this type of stuff. So sometimes it can get a little bit confusing. And some questions we might ask is, how do we optimize with respect to vectors? Because in calculus, you might have seen how to optimize with respect to like scalars and things like this. And how do we combine both fields of linear algebra and calculus? And how does this all kind of relate in machine learning in itself? So that is the motivation. And the plan of the talk is that matrix calculus, what I want to convey to you is actually pretty simple. And what I'm going to do is probably for the first half, it's going to be very basic. It's going to be a review of calculus and linear algebra with the applications to ML, and then we'll pick it up with matrix calculus afterwards. I think there isn't a lot too hard about matrix calculus, but I think a lot of it's just related to previous prerequisites. So if it seems a little bit simple in the first half, that's the intention. So let's review calculus and machine learning. And I'm just going to give you the whole entire broad goal of what machine learning is to kind of give you the story. And essentially, the one sentence how I describe machine learning is to learn a function from data that minimizes its loss. And this term minimization is how we involve calculus in machine learning. So the goal is that we're going to learn a function that minimizes loss. And often this function takes in inputs as features and outputs a label. So in the regression case, this label can be an R, and in classification, it can be a discrete set with K classes. And what do we mean by learn a function from data? Well, we can have a bunch of data points here, and we can literally learn any type of function we want. But that isn't kind of intuitive because there might be infinite functions to consider. So often what we do is, how do we learn the true function? Well, we can add a lot more data points in here. So maybe we can distinguish that this green line here, if we add a lot more data, is probably a not good function, but there still might be infinite functions to consider. So what we do is we have some prior knowledge and we restrict it to a function class. And an example of a function class that we restrict it to is we can restrict it to all linear lines. And in this example, all we need is actually, if we restrict to all linear lines, all we need is 2 points if we assume that there's a perfect labeling function that can distinguish between any other linear line. But then there's this trade-off that we often deal in machine learning, where our function class power, our representation power increases, but we might need more samples and more complexity to learn. And this is just kind of like a review of machine learning between this trade-off of function classes and such. So if you have a question, what we often do now is the function we often learn is a neural network, which is a nonlinear function that has this huge representation power and compared to linear lines, but maybe we need a lot more samples and maybe it's a lot more complex to learn. So what does learning a function really mean? Well, let's go back to our linear line situation. And when we restrict to linear lines, there's still infinite number of lines to learn and so on. So what we really mean is that when we have a line here, we characterize this with its slope. Maybe I'll call this W1, or you might have heard like y equals mx plus b. So we characterize this slope by m, and then we also have a y-intercept as well. and this is also a lot of review. So oftentimes we're going to actually just learn the weights of a function class and not a specific linear line itself. So learning a function means learning the weights. And why did I do all that review? Well, let's go back to the goal. Well, the goal now is to learn a prediction function, but what we really mean is the weights of a function class from data that minimizes its loss. And the solution we often do is maximum likely estimator, which is in its name, is we want to find the most likely weights that makes the data the most probable. And this is the formula of MLE, and I hope that everyone has probably seen this in some shape or form. And essentially, we want to find the weights that maximize this conditional distribution. And we can do the same thing by reformulating as an argument problem, and we just take the negative log likelihood. So one type of loss we can consider are like the L2 losses, and this is also known, sorry, as a squared loss. So where we essentially just take the difference between each value and we square these and then we add it up. And this also is just considering our linear regression problem. Okay, and we could easily solve this MLE. And one thing you might know is, why am I using MLE instead of maybe just minimizing the square losses? Because the MLE is a lot more general and it can apply to a lot more problems. And you will see later that we will be doing stuff with this. So here we have is 4 data points. And we want to find a line that goes through all 4 points. So I can plot these 4 lines here. I can rewrite this in vector notation and such. And also, I'm going to assume that there's some kind of inherent random noise. And I'm going to assume that this random noise comes from some Gaussian distribution. So you can kind of think of each point is sampled from some kind of Gaussian distribution with some noise. Because I'm going to assume that you can't find a function that goes through each point perfectly. And so on. And now my goal is to learn a line where the mean goes through all these points, but the variance is this noise over here. And the whole entire talk is not to be an MLE talk and a maximum likelihood estimator, so I will be skipping a lot of the steps, but it's just more like a review of what you've probably seen before. And you can essentially solve for this by plugging in the PDF of this normal distribution, which is your goal. And when you take the ln and you do some steps, the ln will eventually cancel out this exponential variable and such. And some of the other terms don't matter, because what you want is you want to find the weight. You want to find the minimum weight. So any term that doesn't have weights, you can kind of cancel them out. And you get the equation where we want to minimize the squared loss. So hopefully that kind of makes sense, where I said that I'll just go through the MLE derivations because it'll come later. So basically, solving linear regression is equivalent to finding the weights that minimize squared loss when we assume that our noise comes from some Gaussian distribution. Okay, so now we can introduce calculus. So now we actually get to, how do we actually find this minimization? And when we have a loss function, so this isn't the loss function here, but it can be any loss function. One way we can do is we can kind of check every point, and then we can compare 2 points, which one's lower. But obviously we don't do this because this comes to the same story that we might have to check infinitely many points. So instead, what we're going to do is we're going to exploit the smoothness, and we're going to take derivatives. So derivatives is the instantaneous rate of change at a point. And essentially, we're going to exploit this property here. And you can probably already tell that when the derivative is going to be 0, this is probably going to be one of our stationary points. So a derivative is, what I like to see is the instantaneous change in y with respect to x. And the formal definition is that this limit, you take the function values, which we say the change of y, the difference, divided by the change in x. And that's what would also be characterized as the slope formula. So one example of derivatives we can do, just as a quick review, is we have this function y equals 3x. We can look at every point, find the instantaneous rate of change at that point. Alternatively, we can just plug this formula in, and we get that the derivative is equal to 3. And then just to be clear, this formula is you've often seen a table of different derivative formulas. It's all derived by this. One thing here, though, as you can see, is that this graph has no minimum. Another thing we can do is we can take the parabola and do the same thing. And here, the derivative is equal to 2x. And there is a minimum that exists, and it's right over here. So visually, whenever our derivative is equal to 0, our rate of change at that point is nothing, and that's when our potential minimum or maximum occurs. All right, I'm going to see if we have any questions with any of that. Okay. Looks like we don't have any questions, so hopefully that was all clear. All right, so that's just a basic derivative and a basic review, but we might ask now, like, what if f is not basic, it's not simple? We can take in multi-variables, but we still output something in R. And this is where I like to reformulate how we kind of think of derivatives. Instead of saying the change in y, because this will be related later, I kind of like to think of this as the instantaneous change in the function output with respect to the change in input. Because f could also maybe take in matrices or take in vectors. And our change in input might be a matrix or a vector in itself. And one example you may have seen is things called partial derivatives. So now f is not that simple. We can take in multi-variables. And now we want to find what's the change in output with respect to maybe one of the variables changing. And this here is essentially the same linear regression thing we derive from the MLE here, where we had two weights. We had the slope and the y-intercept. So what we might want to do is we might want to find the partial derivative with respect to only one of these weights changing. And what we can do is we can take these partial derivatives, and essentially a partial derivative with respect to W naught is you're going to treat the other variable as a constant, and you're going to use the same derivative rules. So here to take the derivative, what I'm going to do is I'm going to use chain rule. I'm going to do this power rule, bring this 2 over, and then take the derivative of the inside with respect to W naught, which is just 1. So that's how I derive that. And then the other one is the same thing. I'm going to use this chain rule. So first I'm going to do a power rule. It'll be that. And then I'll take the derivative with respect to the inside, which should actually just be, my bad, should be x1 or x. Okay. And another thing we can do is we can have something called gradients, which is a vector of partial derivatives in itself. So these are each partial derivative with respect to the input variable, which we're going to fix one variable and take the partial derivative of the other variable. And now we can have a gradient where we can have all the partial derivatives in one vector. And this is also something you may have seen. And then I'm just going to say there that derivatives are linear operators because sometimes we deal with sums, take the sum of all samples, and then we want to take the derivative inside the sums. And the reason why we can do this is because derivatives are linear. So once again, going back to this linear regression example where we had 4 examples here, we can define this as our loss function. And remember, the goal of machine learning is to learn a function that minimizes its loss. The reason why this is the loss function, and maybe I wasn't clear earlier, was that this portion here is essentially your predictive value, which was your f of x, minus the true value, which is y. And this is what's going to characterize the loss. And we're going to sum it over all samples. Okay, so now we want to minimize the loss. So what we're going to do is we're going to actually take the derivative with respect to each partial variable. And then we're going to set this equal to 0, because that's when our stationary point is going to occur. So here, what I can do is I can move this operator inside the sum, because I mentioned earlier how derivatives are a linear operator. And notice how each partial derivative here, we actually calculated earlier as an example. So you will see throughout this whole entire talk, I will be reusing the same example. And then what we're going to do is we're going to set this equal to 0, and then we're going to solve for the weights. And we could solve this in closed form. And the way you do that is this essentially is a vector. You can translate this as a matrix, and we will see how to do this later, as AX is equal to B. But I just want to note that oftentimes we don't solve this in closed form, and we use something like gradient descent because closed form may not exist, or it might be computationally inefficient. So the one way that gradient descent kind of works, and visually it's pretty nice, is we can have a point here, maybe WT, and what we're going to do is we're going to look at its derivative, and this essentially is going to push it into the direction of a stationary point. So here the derivative is decreasing, and we're going to have minus something, which is essentially going to be plus something, and it's going to move this WT closer and closer to the stationary point. And alternatively, if the derivative is increasing, we're minus an increase in value, and it's going to push the stationary point to, push our weights to the stationary point. But one question you might ask is, why does this work other than maybe like a visual intuition? And the real reason is Taylor series. So Taylor series is one of the most important theorems in statistics. In fact, usually my statistics professors say that the 3 most important theorems are central limit theorem, weak law of large numbers, and Taylor series. Why is Taylor series very important is because we can approximate any function, assuming that it's n differentiable, which we can choose our loss function using its derivatives. And for this case, in order to show why this kind of works, what I'm going to do is I'm going to assume that our weights is scalar. We can rewrite our loss function in terms of all its derivatives, and this is just the Taylor series formula. You don't have to know too much about what's going on with the math here, but essentially we can approximate this just using the first derivative and the second derivative. And then what we're going to do is we're going to take the derivative of this loss here, and this derivative becomes 0 because it's not respect to W, it's respect to WT, and so on. And we can write it like this. And what we want to do is we want to set our derivatives to 0, and then we can solve for W, and we get this type of equation here that looks like our gradient descent update. In fact, this equation here, people might consider this as the second order update, or what we like to call the Newton-Raphson optimization method, where here our step size is going to be our second derivative. Now, normally we don't use the second derivative for our step size, even though it's probably going to be better, because the second derivative is going to control our curvature and tell us the shape of it, but we usually can't calculate this or it's too computationally inefficient. So that's why this works. But oftentimes when we introduce why gradient descent works, what we do is we assume W is scalar because we don't introduce things like matrix calculus. So you might have questions. How do we differentiate with respect to a vector? And also, what if we had different functions? Like maybe we inputted a matrix and we took it with respect to another matrix. And then how is this all related to machine learning in itself? To give you a quick review of linear algebra, well, clearly linear algebra is very useful. In this example here, I only work with one feature, which is the house size, and I was going to predict the house price. But in practice, we're going to have lots of features. We might have house price, location, number of bedrooms, and such. We're going to learn a weight vector, or nowadays we call these weight matrices. And also linear algebra can reformulate some of our notation. So here I can reformulate the linear regression in terms of vectors or even matrices, which this is in fact going to be a lot better. And a lot of linear regression, like graduate level textbooks, will do it in this way because to do the optimization is much better to do it with this notation here. And instead of giving you the whole review of linear algebra like I did with calculus, I'll just give you some useful examples, and we'll see these examples when we actually going to do matrix calculus. So one thing to know is that matrices are linear transformations. So when we're going to have our data matrix with n samples and d features, and what we're going to do is we're going to learn a weight, essentially what we want to do is we want to transform an input vector to some output, and this output's going to be our prediction. So a question you might ask is, how do you take derivatives of this matrix transformation with respect to a vector? And I'm just going to pause in this slide here. What exactly does this kind of mean? Well, a matrix transformation here is a function. It's going to take in a vector and spit out a new vector. So clearly this is kind of makes sense because we can take derivatives with respect to functions. Like how does the rate of change of a function output change with respect to its input? Another example that's really useful in linear algebra and machine learning is this thing called dot product, where we can take in two vectors and then we can multiply each element and add them up. And the intuition of dot product itself is you're going to have a vector u and a vector v, and what you want to do is you want to project the vector v onto u, and you're going to multiply these two lengths together, and that's the dot product. And the reason why this is very useful is because if the dot product is positive, we like to say that they're kind of like similar to each other. If they're zero, here, when they're orthogonal, we project it onto this vector. Clearly the length is zero. So sorry, I meant that when you project the vector v onto u, you're going to multiply the two lengths together. So when the dot product is when the vectors are orthogonal, you're going to project it onto here. The length is zero, so that's how your dot product is zero. And then when they're this angle over here, they're going to be negative. So when they're far apart or not similar to each other. And you see this in things like large language models. If you can treat each token as a vector, you often ask, how are these tokens similar to each other? How are they not? And this is how we do. We just take the dot products of these. And then this is the notation of dot product. Sorry, this is another example in our linear regression scenario. We can have a vector of weights and a vector of each feature, and we're going to take the dot product of each other. And I can kind of see that this notation is kind of bad right now. But for each sample, we can take the dot product of each other. So another question you might ask is, okay, how do you take the derivatives of a dot product with respect to a vector? And a dot product is a function itself, so this is something that we should probably be able to do. Okay, another useful thing that we have in linear algebra is norms and lengths. One thing to note is that a dot product, or something more general we call an inner product, can induce a norm. And basically that means that whenever you have a dot product, you can define your norm as the square root of the dot products together, and that's going to be your length. And like the visual intuition of that is if you had a vector here and another vector here and you project it onto itself, you're going to multiply the lengths together, and then you're going to square root this, and that's going to be the length of one of them. So one thing we can write is that the norm squared is equal to the dot product. And this is also very useful in machine learning because we might want to ask, what is the length of your whole entire weight vector? And the reason why we do that is because we can have some samples here, and maybe we consider a function class of all polynomials. And maybe it's something like this. And this example here is an example of overfitting, and we might want some of these weights to be close to zero so we can get maybe a more smoother function that goes to our points. So we can add something called a regularization, which is essentially a prior. So instead of considering the MLE, we're going to consider called map. I think it's called the maximum A something. I forget the whole entire name. But instead of finding the probability of the data given the weights, you're going to say, given the data, what's the weights that make my thing most likely? But you can use Bayes' rule and essentially reformulate this in terms of the MLE times the prior. Example of this is a linear regression with a Gaussian prior. So here we're going to assume that our prior is Gaussian, and when you do the math and you get like the 1 over 2 pi square root, the exponential, and do all that, you're going to, with this Gaussian prior, you're going to get this term over here. And you can see that we want to find the weights that make this minimized. So we don't want this term to go too big. And we're going to penalize some weights of this that go too big because we want to minimize W essentially. So if this vector was something like this, we might want to penalize some weights and push them closer to 0. So the question we might ask is, okay, how do you take derivatives of a norm with respect to a vector? And lastly, the last example we're going to look at is something called quadratic forms. I like to think of quadratic forms. So earlier I introduced something called dot product of norms, which essentially is going to be the length of your vector. And a quadratic form is a more general dot product. Because instead of now just the vector transpose times the vector, we're going to put this matrix in between the two vectors. The quadratic form, it's still going to spit some number in R. But to give you an example, if we had a 2 by 1 vector and a 2 by 2 matrix, and we write out this whole vector matrix multiplication, we're going to get these cross terms in between. So in a dot product, we only got the x1 square and the x2 squared, so only these terms. But now in a quadratic form, we actually get these in-between terms, which makes them a little bit more informative and a little bit more useful. Now, quadratic forms are used all over in higher dimensional vectors, matrices, optimizations. You see them a lot. Most textbooks, you'll see this in the first chapter. You won't maybe know why, the intuitive reason, but it's because they're a more generalized dot product and they're suitable for this higher dimensional optimization. We will see some examples later too. So now how do you take a derivative with respect to the derivative of the quadratic form with respect to the vector itself? Okay, so now that was the first half of the talk, which was just basically a review of it. Now we're going to actually get into matrix calculus itself, and the whole entire goal is to show that, well, matrix calculus isn't as hard as it seems. It's just a combination of the two, but oftentimes it's neglected in our current curriculum. So things we've seen was derivatives, partial derivatives, and gradients. And so the derivative is maybe we can have one loss function, and we're taken with respect to a scalar x. A partial derivative is we can input multivariables like a weight vector, and we want to take the derivative with respect to one of the weights itself. And the gradients is we can have a vector of all those partial derivatives. And I'm just going to pause here to see if there's any questions with what I explained before as all the review topics. All right, seems everything is good. So one thing I'm going to introduce now is Jacobian, which I like to call this as the generalized first derivative. And a Jacobian basically is instead of in partial derivative we had one function, we're going to have n functions here, and we're going to take the partial derivative of each n function. So here you can think of this as just one function here, and this is the gradient of just that one function. And we're going to do this n times. And you're going to see Jacobian being a little bit useful here. We don't typically use Jacobian too much in machine learning, because normally in machine learning, we just deal with one loss function and not n loss functions in itself. Although this is changing a little bit, because now in more recent literature, instead of dealing with one agent, we might deal with like n agents. Each agent has its own respective loss function. Maybe you're modeling something and that has like n different agents with maybe even n different loss functions. And you might want to use this notation of Jacobian in itself. Because a gradient it's just going to tell you the partial derivatives as just one function. The reason I like to call this like the generalized first derivative is because assume that we didn't have all the other functions, then essentially what we're going to get is just basically the gradient. And then also assume that we had only one function and we had from R to R. So we're only going to have one partial derivative, which is going to be the first derivative in itself. Okay, so Jacobians are just the first derivative, or a generalized first derivative. The next thing we might see is something called the Hessian, which is the general second derivative. And essentially what it is, in a Hessian, I'm only going to consider the case where we're only going to have one loss function. And when we take, so the intuitive thing is we take the gradient of this again. Hessian is going to give you a matrix of all the second order partial derivatives. And I like to call this the generalized second derivative. So you might ask, okay, what if we had this case where we had n loss function in itself? Then is it going to actually be hard to kind of visualize what the Hessian is? We don't call this a Hessian, we actually call this tensors, and normally we don't even deal with tensors in machine learning itself. So that's what a Jacobian and a Hessian is. Are there any questions with that? Okay, looks like we're fine. And so one thing I got confused with when I was learning this a couple of years ago is that we have this like double gradient operator. And what does this really mean? Well, I introduced something earlier, which is called the inner product, where we take the vector multiplication of its transpose and itself, and what we get is a 1 by n vector times the n by 1 vector, and we're going to get a 1 by 1 thing. And this is going to be something in R. There's also something called the outer product, where we might want to build a matrix. And instead is we're going to take a vector times its transpose in the flip direction. And visually what we get is an n by 1 vector, a 1 by n vector, and we get an n by n matrix. So in the Hessian, what we actually want to do is we don't want to get a 1 by 1 second derivative. We actually want to build a matrix of all the partial derivatives in itself. So the Hessian is really the outer product, where what we're going to do is we're going to take the gradient transpose of the loss function, so this section right here, and then we're going to take another gradient of itself. So that is what we mean by this. When you actually look at the so the gradient transpose, when you actually like look at it out, that's how you get all these like these notations here. That's how you get W1 comes first, W2 when you do the formulation in itself. But that's kind of what we mean over here. This notation is just going to be the outer product, and that's how we build the matrix. Okay, so now we're going to get through some matrix calculus identities. And normally in calculus, you are actually going to derive these formulas from that limit formula I showed earlier, and then you're going to have some kind of formula sheet, and then they're going to say, okay, it maybe just like memorize all these formulas, or you don't have to keep deriving that limit. And it's very similar with matrix calculus, but what exactly are the rules? So there are these rules and formulas that we need to know. So I like to make this analogous connection here. In calculus, we might want to ask, okay, what's the derivative of cx, where c is a scalar and we're taking with respect to x? So here we're going to have a line, and the derivative is going to be a constant c, because the slope is going to be the same for all points. So another question we might ask is, okay, what's the derivative with respect to the vector changing of this dot product? And this is one of the motivations that I introduced earlier in the linear algebra review. Okay, and in order to do this, what does it actually mean with this vector changing? And that's like, so one way we can learn matrix calculus is I'll just show you all the formulas and so on and just go memorize, or maybe just have that in handy, but it's not really intuitive and doesn't really actually tell us a lot. The way that I like to teach matrix calculus is I like to take the more intuition route, and what does it mean for a vector to change? So we might have a vector here, x1, x2, and so on to xd. And normally in calculus, we have 1x, and we want to see how it changes when we get close to it. But what does it mean to get close to each vector? It really means to get close to each element here, but we have to treat one separately, like a partial derivative, like a gradient. So what do we really mean by derivatives with respect to a vector? We actually mean gradients, where we fix one variable and we see what's the change in output with only that one variable, and then we consider every one of them. Instead of just seeing how the whole entire vector changes, that's not how derivatives work. So we can expand this dot product in terms of here, and in this case, a derivative is the gradient with respect to the vector. And the gradient of this formula over here, so we can do the first one, the partial derivative of f with respect to x naught is just w naught, because everything else you can treat them as constant. The derivative of constant is just 0, so these are all 0, those are all 0, and that's how you get this first element here. And you can do the same, so the derivative of f with respect to now x1 is just going to be w1, and then everything else is just going to be 0 because we treat them as a constant. But hopefully that kind of makes sense, that when we deal with vectors, when vectors are changing, what we really mean is gradients. Because if we scroll up over here, gradients is just the partial derivative of each variable. Like ideally, each variable kind of changes as we get close to the vector x, but that doesn't really make sense because how do we deal with all d variables changing at once? So what we're going to do is we're just going to fix one. So in the end, for a dot product, for this here, when we take the derivative with respect to x, what we're actually going to get is the weight vector in itself. So there's that result, and they're very analogous to actually calculus in itself. And this is like the really interesting thing, is that in calculus, when we take, oh wow, okay, this should be C. In calculus, when we take the derivative, what we're going to get is we're going to get that constant, and here we take the derivative with respect to the vector, we're just going to get the weight vector itself. And we don't actually use this notation, ddx. I just like using it because it looks very similar. What we're actually going to do is we're going to take the gradient, because what does it mean to take the derivative with respect to a vector? It actually just means the gradient in itself. Okay, now we might go to the next question. How do you take derivatives of a linear transformation with respect to the vector x? And hopefully I've brought up the whole entire intuition that really derivatives actually just mean the gradient. Maybe not in this case, we'll see. Looks like some parts of my slides got, okay, I don't know what that's doing there, but anyways. So like I said earlier, this linear transformation is a function, so we should be able to, take the derivative of this. And for simplicity, what I'm going to do is I'm just going to do it in this 2x2 notation. I'm going to use very simple matrix and vectors. And you can actually, by the way, derive all these matrix calculus identities or rules that we're going to get in general using like summation notations and things like that and partial derivatives. But rather than looking at notations, let's just look at very simple examples, and it does generalize. So maybe just trust me on that. So here, A times x, a matrix A times the vector x, is the same thing as this over here. And we can treat, so we're going to get a vector. So we're going to get a matrix, a linear transformation of a vector to a vector. We're going to output a vector. And we can treat this as maybe like our first function, f1, and we can treat this as our second function, f2. So now we're dealing with two functions, so multi-functions, and this gets very similar to what we did earlier with Jacobians, where Jacobians is the generalized first derivative when we might have more than one functions and also more than one variable here. So in this case, the derivative, and I'm going to use this notation called the denominator layout. really doesn't really matter, just how you define what the derivative is. Don't get too worried about that. In most literature and machine learning optimization, we use the denominator layout, which is the Jacobian transpose. Some other literatures and math, they will use, they're called the numerator layout, which is just the Jacobian. And I will show you what exactly that means. But what I want you to consider is that the Jacobian transpose, if we actually go up here, and what is the Jacobian? If we only look at one function, the Jacobian transpose is exactly the gradient itself. So if we do the transpose of this row vector here, we're going to get this column vector here. So that is why in machine learning and optimization, we do this denominator layout where we do the Jacobian transpose, because it makes these columns here, which I'll show it, it makes these columns as gradients rather than rows. And in matrix, we often care about the columns because we like to take the linear combination of the columns of a matrix. So essentially what we're going to do is we're going to define the derivative of a linear transformation with respect to x as a matrix of these partial derivatives. And this here is the gradient of the first function. Maybe I can say this is the gradient of f1. And this here is the gradient of f2. And in this example, when we do maybe this case here, we're going to take the partial derivative of f1 with respect to x1. What we're going to get is just a. And we're going to get here is c, b, and d when you do all of them out. And this is actually going to return your matrix transpose. So it's very interesting that it's very similar to in the calculus case, in the sense how if we take the derivative with respect to a vector, we're going to get w and w transpose. And notice how this is w transpose and we end up getting w, and this is a and we get a transpose, because we're doing the denominator layout for this talk. But also, we don't usually use this notation, ddx. It's actually very bad notation. What we instead do is we use gradient. And even this in itself is bad notation, because we're not really taking the gradient, we're actually taking the Jacobian. But this is a little bit more common what you see in ML literature. Sorry, this one over here. Okay. Now the next question we might ask is, how do we take the derivative of the dot product in itself? And there's a very analogous relationship to the parabola in the normal calculus case. And very similar. So like I said, you can actually derive all these rules by if you just expand everything out, use the summations and take partial derivatives and so on. So what I'm going to do is I'm going to expand this dot product out, which is going to be this here. And in this case, the derivative is the gradient because we're taking it with respect to a vector. So hopefully I've slowly ingrained that. And when we actually do the gradient, let's just do this case here. Sorry, let's take the derivative of f with respect to x1. What we're going to get is we're going to get 2x1 for this here, and everything else will be 0 because we're going to treat them as constant for this one over here. So we're going to get 2x1, and we do them throughout, we'll get 2 times that variable we're taking the derivative with respect to. All right, so this is going to be 2 times the vector. And to give you a nice little good comparison, it's very similar here as well. So there's a lot of analogous relations. That's why they maybe don't teach matrix calculus in the curriculum, because all you have to do is just generalize what you've learned in both subjects. And lastly, we might take the derivative of a quadratic form. And for simplicity, what I'm going to do is I'm going to assume that A is a 2 by 2 matrix and our vector is a 2 by 1 vector. I'm going to do this quadratic form. We've actually written out the expansion of that when I was showing you the motivation of quadratic forms and how it's like a generalized dot product, because we have these cross terms. And here we have one function with different variables. So here the derivative is the gradient because we only have one function, but we with respect to different variables in our vector. All right. And when we actually do this derivative, so the quadratic form is a little bit more complicated case, but essentially you take the derivative of f with respect to x1, you're going to get this here. So this term becomes 2a x1. This term becomes bx2. This term becomes cx2. And this term is just 0 because it's not dependent on x1 whatsoever. And similarly, if you do this, taking the partial derivative of f with respect to x2, you're going to get this over here. You can rewrite this in terms of a matrix times a vector here, which is what I did. So for example, if I did 2a, if I did this row times this column, I'm going to get this right over here. And if I did this row times this column, I'm going to get this over here. And the reason why I did that is because there's this nice property that if you do A plus A transpose, you're going to get this matrix over here. So essentially, your gradient of your quadratic form is A plus A transpose times your initial vector. All right. And now you might be asking, how is this analogous to 2x, which is these cases over here? Well, I'll let it pause for a little bit to think about that. If A is symmetric, and symmetric we mean that the transpose is equal to itself, so it also has to be a square matrix in itself. But if A is symmetric, then these two are the same thing, and we get 2ax. And this slide over here, turns out that in machine learning, you typically only need these 4 rules when we ever do optimization in higher dimensions. Now, there's a whole entire rule book of matrix calculus that is like a ton of pages, a ton of chapters, but in most cases and all cases that I've seen, you only need these 4 rules, and it comes down to the fundamentals of what exactly are they. Well, this here is the dot product, this is the linear transformation, this is a norm, and this is the quadratic form. And these are all that you really need to know, so that's why I kind of slowly built this talk up. Okay, but to actually give you the precise definition of what each derivative is, I can for sure give it to you over here. So the derivative of f with respect to a vector is just its gradient itself. So I'm going to define this operator as this gradient, because this here is just not great notation, but you will see that sometimes as well. Okay, now a derivative of a multivariate function. So remember, we're going to have a lot of different functions, like f. I showed the example we had, maybe we had n loss functions instead of 1 loss function. With respect to a vector here, what we actually get is we get a matrix here. And then this is like the formal definition of it. Although I don't really like to memorize or even see all these formal definitions, because oftentimes later in the future, I'll forget about it. Now you might be asking, well, we didn't actually do a derivative with respect to a matrix. So what does it really mean to take a derivative with respect to a matrix, the matrix changing? Well, just like the vector, you can't make all the vector elements change. We looked at each individual vector element that changed. So same thing in a matrix. We're going to look at each individual matrix element that's going to change. So a derivative of your function that inputs a matrix with respect to a matrix is just going to be a matrix of partial derivatives with respect to each individual matrix element changing in itself. And the reason up here I said denominator layout is that this is the layout how we do it. But I don't think it's too important. It's just different notations and different communities. Normally in machine learning, 99% of the time we do this layout over here. So this is the formal definition of it. But rather than like memorizing these formal definitions, what are some tricks? And there's this dimension trick that doesn't really get talked about, but if you have basically, you look at your numerator, the dimension, and you look at your denominator, and the derivative output is just going to be the multiplication of it. So here we have a 1 by 1 and an n by 1. So the derivative output is actually going to be an n by 1 vector. Similarly here, we have an n by 1 and an n by 1. So now the derivative output is going to be n by n. So rather than memorizing the formulas, I actually like this trick in itself. It tells you what the output will actually be. Will your output be a matrix? Will your output be a vector? And so on. And so once again, we have a 1 by 1 and n by 1. The output is going to be n by 1, and so on. Now, another trick, another thing you often see that's outside of just memorizing all these formulas is, why can we always assume that A is symmetric when we do optimization? And you will see this a lot of times. A lot of people will just say, oh, just assume the matrix is symmetric. Because if the matrix is symmetric and we go up here, what we end up getting is we get this nice 2ax instead of A plus A transpose x. So a lot of times in literature, they'll just be like, okay, just assume the matrix is symmetric. And I never really understood this. Like, why can't we just assume the matrix is symmetric? And the reason is because we can decompose any matrix in terms of a symmetric piece and an anti-symmetric piece. And for the sake of time, I'm just going to show you the intuition, but I do have the derivations out here, and I might share the slides, that when we actually do an optimization of it, the anti-symmetric piece, we end up getting this equation here, because we can decompose our matrix in terms of a symmetric matrix and an anti-symmetric matrix. So I use the notation S as a symmetric matrix, and then I use this like S complement as anti-symmetric. And what does it mean for anti-symmetric? It just means that the transpose is equal to the negative itself. And then when you actually do the derivations and you get this quadratic form where we're taking the derivative with respect to a vector, and all I'm going to use these formulas here. This here comes from this formula here. Sorry, I meant this formula here comes from this formula here, because we assume that S is symmetric. And this formula here to here comes from here. But because S complement is anti-symmetric, this part here is equal to negative S, and this is equal to 0. So whenever, basically, the moral of the story is that whenever we do optimization for quadratic forms, if A is square, it doesn't really matter if it's not symmetric or not. The optimization just becomes this part here. And that's why we can say, oh, just assume that it is symmetric. All right, so let's actually give some examples of how we actually apply matrix calculus and machine learning for the next 5 minutes. And sorry, it might be a little bit rushed. So one example we can do is I can just say, what is the gradient, or what is the derivative with respect to a vector x, which we may actually mean is the gradient of maybe this equation over here. And if you just apply these rules, you're just going to get this answer over here. Another question I might ask is, okay, it turns out that this transpose operator in linear algebra, you can bring it inside. And you've probably seen this in your linear algebra literature. So you might ask, okay, what is the derivative of x transpose A, and instead of doing things like AX? And in order to do that, well, let's take the transpose of x transpose A, which is A transpose X. We know the derivative of AX is equal to A transpose. So the derivative of this is just equal to the transpose of that, which is just equal to A itself. But since we did the transpose of it, let's take the transpose of this again, and that's how we get the derivative out of it. And my apologies if this is a little bit rushed. Okay, so let's revisit optimization. So one of the questions we asked is, okay, why does gradient descent kind of work? And we assume that W is scalar, but now we can actually assume now that our weights are a vector. And we can use the multidimensional Taylor series to approximate it. And I'm going to use it using just a second order Taylor series approximation, but now this is higher dimensional. So this here, remember, our gradient is like our generalized first derivative, and our Hessian is our generalized second derivative. And what you can do is you can take now the derivative of this using these matrix calculus rules over here. So you'll actually notice that a lot of times when we apply matrix calculus, it's just really using the rules over here. And we can eventually get the same equivalence that we got when we assume that W is scalar, which is this formulation over here. And then if we assume that our step size is the second order generalized derivative, then we get the exact same thing. But we don't do that because finding the Hessian matrix is not computationally efficient, and in most cases, it doesn't actually even exist. Or maybe sometimes it actually does, but it's not computationally efficient. Okay, One thing we might want to ask is, like, how do you know if your stationary point is the minimum? Because I said that it's whenever our derivative is equal to 0, it's a potential minimum, maximum. It could even be a saddle point, or it can be inconclusive. And for Calc 1, there's the second derivative test, that if your second derivative is greater than 0, because your second derivative controls the shape of it, or your concavity of it, then if this shape is positive right over here, then this indeed is a local minimum. And we can have the same exact equivalence analogously for using second derivatives, which is from quadratic forms. So if this is actually greater than 0, then basically your stationary point is the local minimum. And equivalently, it's when all eigenvalues are positive. I would like to say this, the intuition of it, but I don't have enough time. But your eigenvalues essentially control like the stretch of any vectors that don't get changed from your linear transformation. Okay, so really quickly, okay, what about like models? I showed you the derivations of Taylor series. So linear regression, we can rewrite our linear regression in terms of matrix notation. And then the whole entire goal is to solve the difference of squares. But now we can actually apply the matrix calculus literature, and there's a good like geometric viewpoint of how you solve linear regression, but unfortunately I don't have enough time for that. But all you do in terms of applying matrix calculus, you usually just apply this rule. So when I take the derivative here and this step over here, which I am skipping a lot of steps, and I set it equal to 0, the way I actually take the derivative is I'm just applying the rules here. And you can actually find out the solution for your weights, which is equal to here, and there's a whole entire geometric point of view as well. And you can do the same thing with like linear regression with regularization, but instead now we're taking the gradient of a regularization term as well. And this regularization term, the gradient is just 2w. So I get 2 lambda w here. And then if I do the formulations, I get something like this. So this was just basically an introduction of matrix calculus, kind of get an intuition of it. It was a lot more basic, but why is matrix calculus actually important? Well, it's used in higher dimensional optimization everywhere, like deep learning, where maybe we even have things like weight matrices and not weight vectors, specific topics like normalizing flow and MLE and singular value decomposition, principal component analysis, Gaussian process, and such. So I often said that, okay, you can reference a rule book, but maybe knowing the good intuition is good first. These are like the 2 key cornerstone resources that I use. So one of them is called Matrix Cookbook, which is basically like it has all the rules that you'll ever need to know. But in fact, from these slides, those 4 rules that I showed at the start is basically all the rules you need to know, plus maybe some caveats. And then if you actually want to see a course, recently it's being introduced in things in our curriculum. Like MIT offers this course called Matrix Calculus for Machine Learning and Beyond. It is a really good course if you want a whole comprehensive, detailed overview of matrix calculus. So that is basically my talk. Thank you so much for joining me, and thank you to the organizers for inviting me as well. Oh, and we do have a question. I was going to ask about the matrix calculus MIT course. What is how it's simple? It's basically like a whole entire course that goes through the formalizations of how to derive all this type of stuff. Look, one of the actually main examples, and I think I remember the main reason why that course was started was because students often asked, how do you actually formalize finding like a derivative of your linear regression loss function and things like this? Could you please drop the links to the book and the course? Oh yeah, I will for sure do that. I will for sure do that. But yes, the course also comes with lecture notes and videos as well, and it's really good. There's also another paper I will put it in the Discord. It's something like matrix calculus for deep learning. It was, I think, published in 2018. That's also pretty good as well. But I will drop all the links in the Discord as well.
Thanks so much for coming. That was a really amazing talk. It's nice to see how we can incorporate the calculus and linear algebra together in matrix calculus and exactly how it works in machine learning. So thank you for the very thorough explanation.
Yeah, thank you so much for inviting me. And also there's one more question. How do you deal with taking derivatives of non-trivial questions? Yeah, thank you so much. That's actually a good question. And usually I waste a lot more time when I take derivatives with respect to matrices and vectors. The one way I do that is the way that I kind of explained it here. I just start with a simple case, like I simplify like x as a 2x1 vector and a matrix as a 2x2 matrix, and then I'll do the derivative from that. So even if it's like a really long equation with a lot of matrices and a lot of vectors, I'll simplify it to the beginning one, and then I'll do that. The other way is just what most people do and most researchers is just use the matrix cookbook, and the rules are very similar to the rules you learn in calculus. So like there's like chain rule and product rule and so on and things like that. And most times in like if you have never seen matrix calculus, and most times in literature, it's actually just going to be in the appendix in itself when they put their proofs and their theorems and such like that. The remark about symmetric matrices are interesting. Yes, you can assume your matrix is symmetric when you're going to do an optimization. This is actually, I agree, it is very interesting. And it's something that, like for years, people would just say, oh, just assume your matrix is symmetric. So you do have to assume that your matrix is square, but when you are doing optimization of a quadratic form, your matrix can decompose into two parts. And their second part becomes 0. Does that apply to everything? I guess my answer to that is it depends. But hopefully I answered that. Okay, I'll wait a couple of minutes to see if there's any other questions. Yes, that is a good question. So I definitely oversimplified it to show you an easy way how to explain matrix calculus, but the more formal way is when you deal with operators like Kronecker products and things like that. And that is actually what this course will actually kind of goes more into detail. There's another playlist that kind of goes through everything a little bit, but I kind of like the course a little bit better. But that is a good point. So when I did say that just assume that things generalize, we'll assume from the simple case, it's because things like the Kronecker product does generalize for any finite dimensional n.